less of the emission because the orbit is processed away from the line of sight. So in any given detector, that means because of the precession going away, because the orbit has gone away from the line of sight, you see a smaller amplitude of gravitational waves at a detector. And then, then it can process back again, and if it processes back into the line of sight, then the magnitude, then the amplitude of the waves of the detector will increase. So this is like a slow variation in the amplitude of the gravitational waves. Okay, I'll put out the phase. So if you look at this, the purple curve, you start off at a large amplitude, it goes to a small amplitude, it goes to a large amplitude, kind of the envelope. So imagine the original sine wave multiplied by an envelope which itself is varying over time. But this the variation in the amplitude is happening much slower than the oscillation of the orbit. The oscillation which is just due to the orbital motion. So, I mean, this is a very distinctive signal, and if you're able to observe it, you can definitely, if you're able to observe this modulation in the amplitude, you can certainly say a lot about the geometry of the system.
I was going to just add that in addition to the amplitude modulation, because you're going from circularly polarized to linear polarized, you also get phase shift.
Yeah.
And you get a phase shift in there as well. I don't expect you to be able to draw it, but I just want people to know that you also get that effect, so that's another.
Yeah, I mean, there's a number of further smaller corrections to the gravitational waves you get. The better you can model this, the more morphologies you get out of it. But, well, unfortunately, there's a number of things which, for the signal we detected, basically this effect is almost unobservable. Well, firstly, imagine if the detector is here, or if the Earth is there, and if it's being observed along the angle of if the line of sight is along the total angle of momentum, then the orbital angle of momentum will just stay at a constant angle to the line of sight, and then you won't actually see much of this effect. You may see a phase shift, but basically it's possible that even though the system is processing, you won't see that effect of the detector. And then, okay, this is a slow evolution in the amplitude, and if all you see is that part of the signal, it's possible that if it takes maybe 10 cycles to see that the amplitude has changed, but all the paraffin detector is maybe 6 or 7 cycles, you won't be able to see that this has happened. And then the other reason, another technical reason why this is difficult to detect with confidence, basically this means that you have to determine that the amplitude of the gravitational wave changes as a function of frequency. This means that you have to be able to say your detector is calibrated at one frequency relative to another accurately. So, if your calibration, so what does calibration mean? It means that you have some readout of a photodiode at the output of the interferometer. Then you have to do some transformation on this to say that you've measured the strain. So to make sure that this transformation is accurate, well, there are a number of methods that people use to basically measure what is the response of the interferometer. One nice method is you get a laser of a different frequency, you shine it on the mirror, and then just use the photon pressure of the laser reflecting off the mirror, you can move the end mirrors by a known amount. If you can move the mirrors by a known amount and then watch what is the response of the interferometer, essentially that means changing the photodiode at the output and the motion of the mirrors at any frequency you like. So if you've done that accurately, then you should be able to tell the difference between the amplitude at this frequency and the amplitude at this frequency. But if your calibration is uncertain, then you can't necessarily be clear that what you've detected is due to precession, or is just due to slight differences in the calibration between different frequencies.
You have to rule about the thermoelastic noise.
A little further.
It's subtle.
Is it expected to be different at different frequencies? I mean, I guess.
I don't know. You have to do some tests.
But I don't think it's noise, so it doesn't.
The thermal noise on you.
Sure. I think this will contribute. I don't think it makes the response of the detectors different at different frequencies.
No, I don't know.
This is talking about the translation from the strain, from the displacement of the mirrors to the photodiode output. So this is calibration to real signals rather than noise.
But suppose your signal to noise ratio is good enough.
Yeah.
Maybe you can avoid all these technicalities.
No. I mean, the signal to noise ratio is large. That means all the other systematic effects you have to be controlled very, very precisely.
That's right.
So yeah, in that case, you still have to be careful. You still have to include what we do in the analysis is actually when we're evaluating all these probabilities, we also include the probability that the calibration is inaccurate by a certain level. Okay, there are a number of reasons why even if a signal, even if a system is really processing, we wouldn't necessarily be able to measure it. And that's, I think, unfortunately, the situation we have for the signal we've detected. I mean, I'm not saying that it is processing, but we can't tell just by looking at the gravitation waves in the detector whether it is or not. So it's entirely, the signal we see is entirely consistent with having equal masses, let's say 35, and complete absence of any spin. So this was the first numerical relativity waveform to be actually computed back in the 2000s. Equal mass, non-spinning. That waveform would have been completely very good to detect the signal, and it's still a very good match to the signal we see. So, unfortunately, as far as measuring the spins go, and certainly as far as measuring any non-alignment of the spins or precession, we're still almost at the starting blocks. But okay, if you have different masses, if you observe more of the in-spiral phase, if, for example, the total angular momentum is not pointing towards the detector, but is pointing at some angle to the detector, to the line of sight, then you may have some, if you have considered different systems, which presumably will detect in the future, you may be able to say for definite that some of these are processed. Okay, I don't.
So in this event case, you said this total angular momentum is pointing us to the conclusion?
Again, it's not clear. I mean, if it is processing, then it appears that the total angular momentum is pointing at us because we can't detect any precession. But it could be a non-processing system in which the inclination is non-zero. So this is the other interesting plot that people draw, and essentially will look something like that. So for a processing system or non-processing system, you can define the inclination angle as the angle between the line of sight and the total angular momentum. So, in fact, you can think of this as plus pi minus pi, and you can think of the line of sight between us and the system, and you can have the orbital angular momentum going entirely away from us, which is faced away, or you can have coming towards us, which is face on, or you can have it at some angle. And then depending on what angle to the line of sight this is, you have a different, you are deducing a different distance. So the amplitude of the gravitational wave we see depends not only on the distance of the system, but also this inclination. So, okay. I'm just wondering, do you remember how is this parameterized in terms of what the variable is exactly?
You mean
Yeah.
I think it's the angle of inclination at some time interval
Yeah.
just before merger or something like that.
And let's say this is 0, and let's say this is pi, so,
Right.
so
We can look that
I don't think the results depend on the exact definition.
up. Right.
So,
Partly because there wasn't much precession.
yeah. Well, not much visible precession.
Right.
So, okay, the posterior you get out looks like this. Basically, the line of, if you measure just the amplitude of the gravitational wave, nothing else, it could be then the inclination and the luminosity distance could lie anywhere along this sort of strange shaped line. We have a little more information about this. Basically, the detectors are not precisely aligned with each other. They have a slight relative angle, and then the Earth is not exactly flat. So they have slight components of sensitivity, different components of sensitivity out of the line joining them. So if you imagine the line joining the two detectors, rather than all being in the same plane, they are slightly angled away from the same plane. So they don't see exactly the same polarizations of gravitational waves. So, okay, this gives us a little more extra information. So it actually tells you that it's more likely to be, the total angular momentum is more likely to be facing away from us than facing towards us, but okay, at this point, who cares? Well, to put this in a more scientific way, this doesn't tell us very much about the intrinsic properties of the system. This just tells us where it is, where the orbit is oriented relative to the Earth. But okay, the Earth is not a special point relative to the system.
But for element polarized distance will be important.
Sorry?
Yeah, follow-up. Element follow-up.
Yeah, sure. So yeah, if you're concerned about, well, okay, if this was a binary neutron star or neutron star system, and you wanted to be able to point the telescope at it and have some probability of detecting afterglow or gamma ray bursts, well, I think gamma ray bursts are detectable from extremely high distances, but maybe not other forms of electromagnetic emission. So you want to have some idea of what distance this is at. This sort of median distance I think is around 400 megaparsec. So this is a redshift of
It's like 0.02.
no, 0.09.
Okay.
Okay, and this is a long way away, but it's nowhere near the edge of the universe.
Right, and also I think the whole range is from 200 to 600 or something like that
Sure.
in the distances. So again, if you think about it, the errors if you wanted to worry about time delay from formation to merger or something like that, you're only looking at 200 to 400 million years, and that's nothing.
Yeah, so, I mean, the fact that the merger happened at this redshift of 0.9, but with quite a large error bar, but this doesn't tell you how This doesn't tell you when the system was formed,
No.
only that, having evolved over however many millions of years, this is when it got close enough to merge.
But I mean, if it was a gig a year on either side, then that might be an issue, because you have that much time to play with. But at 200 mega years on either side, it's ignorable.
Yeah. Yes. Well, it's just, it's still recent history in terms of
Right.
the universe. Okay, I think this is basically all I should say, try to say and explain about the parameters in terms of where it comes from, but people can try and ask me those questions.
Okay, thank you very much.